All right, more of chapter 6. Now we're going to look at molecular geometry. And the molecular geometry, what we're talking about here is the shape of the molecule. So what it looks like in space. So in other words, it's the geometry, like the shape of that molecule. And we are going to use what's called the VSEPR theory to predict our shapes. And this stands for valence, shell, electron, pair, repulsion. So what it's saying is that the electrons that are in the valence shell, or in other words the outside shell, those electron pairs are going to repel each other. So this is telling us that the valence electrons try to get as far apart from each other as possible. Because they repel. Okay, so we're going to be talking about regions. So we're going to have regions of electrons. And these regions could be bonds, or these could be lone pairs. Both are going to count as a region. And then we're going to specifically state how many are bonds and how many are lone pair regions. And that's going to help us find our shape. Alright, so the simplest shape that we're going to have is just when we have two things bonded. So in this case, we're going to put the number of regions, the number of bonds, and the number of, we'll just say LP for lone pairs. Okay, so on this central atom, I have two bonds, so I have two regions, and there are no dots on here, so no lone pairs. So you can see this kind of looks like a straight line, so we're going to call this shape linear. And the other thing we like to do is state the bond angles. So we're saying, what is the angle between these two bonds? Well, since it's in a straight line, those bond angles would be 180. Now, we don't usually put this on a molecular, we don't worry about the molecular geometry of something that is simple like maybe HCl, because in that case you just have HCl. That would just be linear because it doesn't have any choice if you only have one bond. So if all you have are two atoms, it's always going to be linear. But in this case, this is our simplest shape that we're going to look at, is the linear where we have two things on there. Okay, well, we can go ahead and go to three regions. Looks something like that. So we are going to have three regions, and all of these have bonds, so there's three bonds, and I have no lone pairs. So in this case, this would be my central atom, and then I would have three atoms coming off of it. An example would be like BF3. And then there would be dots around each one of these things. Okay, we're going to call this shape trigonal planar. Or sometimes it's called triangular planar, depending on the book. Okay, but it looks like a triangle, and it's all flat, lays flat. So that's why it's called planar, because everything lies in the same plane. And since there's three regions, we have 360 degrees in a circle, divided by 3 would get me bond angles of 120. Okay, so I'm going to stick with three regions, but now what's going to happen is on this central atom, I'm going to have a lone pair and two bonds. So I still have three regions, two are bonds, but I have one lone pair. Now, lone pairs take up more space than a bond. So like these are big, they take up a lot of space, like a big balloon up there. And because it takes up more space, it shoves these bonds a little bit closer together. So those bond angles are going to decrease down to 117 from 120. And this shape is called bent because all we see is this part, and instead of being straight, it looks bent. Okay, now we're going to go to the next one, which is going to be 4 regions. So I'm going to have 4 regions, 3 bonds, 0 lone pair. Now this one is hard to draw, but it kind of looks like I have one that's up here, I have one that comes out the side, and then I have one of these that's like back away from me, and then I have another one. They usually use like this kind of a wedge to show that it's coming out at you. So I have one straight up, one to the side, one that kind of goes back into the paper, and one that is coming out toward me. And this is called a tetrahedral shape. And the bond angles are actually 109.5, so almost 110. And the reason it's not 360 divided by 4, only getting me 90, is because they can spread out in a 3-dimensional shape. And I'll show you, like in your book, this is what that shape looks like. So I have one up, one coming out, one that's going back into the paper, and one that sticks out toward me. And they use this wedge showing you the front, and instead they use like these little hash lines to show that the one is going behind you. And in 3 dimensions, this is kind of what it looks like. So tetrahedral, tetra meaning 4 sides, and it's a shape, tetrahedral. Okay, we're going to stay on 4 regions. But now I'm going to make one of these a lone pair. And I'll use the hashes like they have in the book. Okay, so I have one that's a lone pair, and then I have this one on the side, the one that's going back, and then this one that sticks out in the front. And this is going to have 3 bonds, 1 lone pair. And this shape we're going to call trigonal or triangular, depending on your book, pyramidal. Because we basically have what looks like a triangle base, and it's a pyramid. And bond angles are 107. And I'll show you in your book. That's this one down here. Here they show you what it looks like flat. This is the triangle base down here, and here they're showing you the 3-dimensional shape. This is a ball and stick model, and you don't see the lone pairs, because if you would make this out of balls and stick, you wouldn't see those lone pairs on there. But that's your pyramidal shape. Okay, and then we're going to stick with 4 regions. But now we're going to have 2 bonds and 2 lone pairs. Okay, so in this case, I still have my central atom, but now I'm going to have 2 lone pairs and 2 things bonded. So this is going to look bent, like our one that we had before, but now the bond angles are even less because I have these 2 big balloons up here. So it's less than 107, and they're 104.5. Okay, now in your book, they just show you, they don't get as specific. So in the chart that's in your book, you can see they give you an example of what it looks like, an example of a molecule, and they tell you the shape is linear and the bond angles are 180. Okay, Then they show you for 3 that you have bond angles of 120. They don't show you, like, if you have lone pairs, what that's going to do to those. So here we have tetrahedrals, 109. They don't show you that this gets smaller. They're just saying, you know, in a real world, in a fictitious world, all of these would have the same electronic arrangement, but those bond angles get smaller because of that repulsion. So this is the 107 and this is the 104.5. Okay, now that's all the more that your book goes. And that's because all of those are ones that obey the octet. However, in your lab, you're going to come across some other shapes. So in your lab, it's going to expand it beyond those ones, and we're going to get some that don't obey the octet. Okay, and the other ones that we're going to have on here, we're going to have 5 regions. So we're going to have 1, 2, so we have 1 up, 1 down. These ones are called the axial ones because they're on an axis. And then I have 3 that are equatorial, meaning these ones lie across the equator, they're flat. And then I would have 1, see if I can turn this to the side. So this is my equator that's flat, and then I would have 1 coming out here and another one coming out here on the other side. So I'd have my axial ones here, and then I'd have the 3 that lie in this one plane here. So I have the 5 regions that are here. And this is called trigonal bipyramidal. And this was 5 regions, so 5 bonds, no lone pairs. And bond angles are all going to be 90 because between top and any one of the sides, between the equator and any of these, that's going to be 90 degrees. And then the 3 that are here, between those are going to be 120. So we're going to have bond angles of 90 and 120. Okay, we're going to stick with our 5 regions, but now we're going to make one of these a lone pair. Okay, so I turned this a little bit, so these are my axial ones, these 3 are my equatorial. One of those becomes a lone pair. And this kind of looks like, if you can imagine a person sitting here and a person sitting here, this would be a teeter-totter. So this is called seesaw. So we have 5 regions, 4 bonds, and we have 1 lone pair. And in this case, we're going to have 90-degree bond angles. Except for this one's going to be 180. Okay, next we're going to have 2 lone pairs. So we have 5 regions, we're going to have 3 bonds, 1, 2, 3, and 2 lone pairs. And this looks like a T, so it's called T-shaped. And bond angles are going to be 90 degrees, so 90, 90, and then between here and here, those ones would be 180. Okay, one section left for shapes. Now we're going to have 6 regions, 6 bonds, no lone pairs. Okay, so I have my 2 axial, and then I have 4 that are sitting along the equator. So these 4 are all sticking out straight. So imagine like you're looking down, those are those 4, and then you're going to have 1 that's going in and 1 that's coming out off the bottom. And this is called octahedral. Because if you could imagine that this was like a square and then it went up to this part, then you're going to have a total of 8 sides. So it's called octahedral. And all those bond angles are 90 degrees. So 90 between here and here, 90 between the axial and the equatorial.